All right, in the last lecture, we saw how do we compute the sign signature of a sesquilinear form, Hermitian or symmetric form. And so far, I have not talked about trace forms. So today I will talk about spectrum and the trace form. So first I want to recall some basic stuff. Most of it will be without proof because it is well known. All right, so this word spectrum, it's a very lot of things are doing by using the spectrum, and it is first I want to show you that this spectrum is not different from the spectrum which one considers in function analysis. So let us start with one example and then I will generalize it. So start with the example. All right, before I start with the example, let me set up the notation. So suppose you have a vector space, V is a vector space. Over K. K is arbitrary field. Now, if you wants, can take real numbers or complex numbers. And suppose you have a linear operator F, V2, K linear operator on. The standard trick to study linear operators on a vector space is by making a V as a modulo over the polynomial ring Kx. How? It's like this. So we have here K polynomial ring Kx. And then we have the endomorphisms of V and KV. And F was an element here. Then I map capital X to that F. So the universal property of the polynomial ring will say that this is enough to define on X. So this way you will get the image of this map. So this is the evaluation map. So this, let me call this epsilon F. Depends on F, the given operator. And then the image of this is obviously K algebra homomorphism. And the image is precisely the subalgebra of end V generated by F. So this big algebra may not be commutative, but the subalgebra is commutative. So this map, it's surjective, and now therefore it will give a Kx module structure on the vector space V, which is defined by F. So that is, if you want, you can take, if you have any V in V, and x times v is by definition this f of t. With that, it becomes a module over kx, and then one, because this ring, this polynomial ring, this is the PID, and therefore we have our and the structure theorem of finitely generated modules over a PID, and then one uses that to study things about linear operator. That is how it was it is done in a standard thing. All right, so this, if this is finite, this V is finite dimensional, then we can apply the structure theory for finitely generated modules over a PID. That was the idea. So it is closely connected to this Kx. The study is closely connected to the modules over a PID. That is, I will not go much into that. But now what we want to do is as you know, so let us look at this again. Let us start with our problem was what? Our problem was if you have a field K is a real number for us, and we have several variables, but I am illustrating with one variable. So this is a polynomial ring, and f is a polynomial there. And our interest was to say how many zeros is polynomial f. So Vk of f is by definition all those zeros in K, x in K, such that capital F of x is 0. This is the set of zeros of capital F in K. So K is real numbers, and we wanted to know what is the cardinality of VK. That was the problem. And not only for one polynomial, many polynomials, many variables. That was the problem. And such that, so more generally, we were interested in finding out this F1 to Fm. What is how to find this? And but we had an assumption that this F1 to Fm, they are polynomials or real numbers in x1 to xn, such that when I go mod this, that was the assumption. Mod ideal generated by f1 to fm. This is a finite dimensional R vector space. That is what. And I want to connect the trace and signature with these zeros. That is the idea. All right. So what we want to connect. So first of all, I will recall what is the trace form. All right. So for that, so to simplify the notation, I will call A This is finite algebra over a field K. I will do some of the things I want to do it more general so that they don't apply for only for real numbers, but they apply it for the arbitrary field K. And when I say finite, that means finite dimension. So this means finite dimensional K algebra. This is a standard terminology one uses in algebra. Finite algebra means finite dimensional algebra. Finite type means finitely generated K algebra. And finite always implies finite type, but not the other. Polynomial rings are finite type, but they are not finite dimensional. All right. Now the tool, classical tool, to study A is the trace form. Is the trace form on A. And it's and several variants of the trace forms. So what is the trace form? So that is a symmetric bilinear form, K bilinear form. I will denote by the letter trace, which is, think of this map form. So it's a trace on A. So it is A cross A. Okay. So this is defined by, take any f, small f comma g, and map it to the trace of now K over A f times g. Now I should tell you what is the trace of an element. All right. So this I should make a little bit more. All right. So let's do that. And not only trace, but I will take the opportunity to recall some of the basic stuff which will be used in this. All right. So you have A, which is finite K algebra. So, and then let us take small x in A. If you look at the evaluation map, Kx to A, capital X to small x. This is the evaluation map at x. Any polynomial will be mapped to f of x. F evaluated at that x. This is again in element 2. X is in A, therefore f of x is also in A because it's an algebra. And the kernel, obviously it will have non-zero kernel. Kernel of this evaluation map is definitely non-zero since A is finite over K. It's a finite dimensional, so you can't have this polynomial, this epsilon x cannot be injective. So that means kernel has to be non-zero. And this kernel is what? Because there is an algebra, this is the K algebra homomorphism. So the kernel is precisely ideal in the polynomial ring. This is an ideal in this polynomial ring, which we know it is a PID. Therefore, this has to be generated by one single polynomial. And that polynomial, the generator will be unique if it is a monic polynomial. So therefore, kernel of X is generated by a single polynomial that I will call it mu x. This is mu xk. This polynomial mu xk is called the minimal polynomial of x over k. And now we can also define what is, so if you take that x, and then we have this lambda x. Lambda x is a multiplication on the left by x. So y going to xy. So obviously K algebra homomorphism. No, K module, K vector space homomorphism. K linear. So it's a linear operator on A. A is a finite dimensional vector space. That was by our assumption. So therefore, it makes sense to talk about characteristic polynomial of lambda x. These I will abbreviate it by just saying chi of x. So this is a polynomial with coefficients in k. Cayley-Hamilton theorem says this chi x actually belongs to the kernel. This is precisely Cayley-Hamilton. And but this kernel is generated by mu. Therefore, so this means chi x evaluated at x is 0. That is Cayley-Hamilton. But kernel is generated by mu. So therefore, mu x divides chi x in the polynomial ring. Actually, one can do it better. This is triviality. This follows immediately for the definition. But one can say a little more about the prime factors of chi x and mu x. But I don't need it, so I will not do it now. Anyway, so now once you have lambda, then we can also talk about, this is a lambda is a K-linear operator, so we can talk about trace of a linear map. But, so I can talk about trace of lambda x, or determinant of lambda x. All these invariants which we studied in linear algebra that are readily available. So now, so what is the trace form? So here, see, you take, so f and g were here, f and g were two elements in K, and the trace of fg means you take a multiplication by f times g map, and that linear map, the trace trace of the linear map. That is well defined. That doesn't, see, normally people will come down to the basis, choose a basis and consider a matrix and consider a trace. But that is well defined, because the matrix, if you change a basis, then there is a transition matrix involved, and then therefore, yes, please. Yes. Anybody has a question?
No, sir.
Okay. Then, okay. So that is a trace. So this means the trace of the map lambda mg. That is the definition. And it is an element in the, because when you take a multiplication map, that's a linear map, k linear map, and therefore when you choose the basis of a over k, then you get to a matrix, and then trace of that matrix, and so on. So that is I've defined. All right, now why don't somebody's mic is on? May I request whoever mic is on, please put it off. Okay. So now I want to connect the trace with the number of points. All right. So what do I want to prove? I want to prove the following theorem. So this is a linear form, not linear, bilinear form. It is symmetric also, because A is a commutative. So trace of FG is trace of GF, and so on. So this is bilinear also, it's clear. Trace is bilinear. And now I want to connect counting the points with the trace. So the theorem I want to prove is, so this is the theorem. The theorem I want to, so A is, so K is R now I am taking. Actually, one can do it more general than R, but then I will have to do more general things. So that may not be, that's not, because the school is linear algebra. So I will have to go out of that. So I don't want to deviate so much. K is R and A is finite R algebra. And for our application, I will take A equal to R x1 to xn modulo those ideal generated by f1 to fn. This algebra. And by our assumption on the polynomials, we are assuming this algebra is finite algebra. That means it is finite dimensional, and therefore I will apply to this algebra. And on one hand, I want to count the number of points. On the other hand, I have a trace and type, signature, and so on. So the theorem I want to prove is signature, sign of the trace form. This is the trace form of K over A. This is what I have defined it here. This one. This one. Let us put here. Like this. This is the trace form. So signature makes sense. And that is equal to number of cardinality of K spectrum. K spectrum. Now I will explain you what is K spectrum. And this will precisely be pk of f1 to f1. So that will give us the way of calculating the number of points, number of common zeros of the polynomial f1 to f1. Now that is the signature. This is the main observation. Okay, that is the one. So, okay, now let us, this proof will not be so difficult, but I have to explain you what is the case vector. So this is case vector. Okay. All right, so I will first start with some examples. So we'll come back to the proof of this theorem. All right. So let us start with the commutative ring. As far as possible, I will do it general. So, okay, may not be so general, but let us start with a finite type K algebra. Typical example of finite type K algebras are the polynomial rings. Ax1 to xn or kx1 to xn modulo some ideal. Ideal A. These are finite type K algebras. And actually we have more than that, we have finite algebra. That means this is finite dimension. But anyway, let's do it because I want to also include the polynomial case. All right. So what is the spectrum? So to be little more precise, prime spectrum. Prime spectrum. Okay. Usually denoted by spec. This is the set of all prime ideals in P, where P is a prime ideal. This is a prime spectrum. All right. This contains what is called maximal spectrum, SPMA. This is a maximal spectrum. Okay. This is the set of all maximal ideals. M is a maximal ideal. And because we know that's easy to see that every maximal ideal is a prime ideal. Therefore, this is subset here. And there was a topology here. There is a topology here. Anyway, I am not going to use all those things, but which is called the reciprocal topology. I am not going to recall that because I will not need mostly. But maybe for motivational purpose, it's easier. So this is a maximum spectrum. This is a prime spectrum. But looks little abstract. So I want to use the fact that it is a K algebra. And how can you produce, how can you produce a maximal ideals in the polynomial algebra? For example. So one easy way to produce maximal ideals. See, one proves abstractly that this maximum spectrum is non-empty. That is Kurutara. It is very easy to prove. But then one might say that can you not produce a maximal ideal concretely? Of course, yes. All right. So suppose you take A equal to the polynomial algebra, just to understand. And suppose I take a point A. A is A1 to An. This is K power N. Then this point will give you a maximum ideal. Namely, ideal generated by x1 minus a1, xn minus a. This is indeed a maximal ideal in the polynomial ring. That is very easy to see because if you go modulo that, you get the field, namely k, and therefore this is a maximal ideal. So points in Kn, they correspond to this special maximal ideal. Well, these are not all maximal ideals. For example, these are not all. One might think that these are all maximal ideals. That's not true. For example, see our field is, our interest is k equal to real numbers. And suppose I take even n equal to 1 and the polynomial x square plus 1. This ideal generated by this is indeed a maximal ideal in the polynomial ring X. Because this is an irreducible polynomial and therefore generate a prime ideal, and that in a PID, so prime ideals are maximal in a PID. So this is a maximal ideal, but this is not coming from a point. So for real numbers, it is complicated. For complex numbers, it is true. That is why these results for complex numbers are much easier. So for k equal to c, yes, and this is precisely the Hilbert's Null-Stellensatz. Known as HNS, short form. I think Professor J.K. Verma is going to say something more about this. So our lectures were, we wanted to arrange our lectures so that one after the other, but due to some avoidable things, we had to shift our lectures. All right. So these are some maximal ideals. These are very concrete ones. And but these are not all. There are more. All right. So also these points also you can think as homomorphisms. See, corresponding to a point A, A1 to An in K power N. We can think this as a homomorphism. This can identify with a homomorphism psi A from the polynomial ring x1 to xn k. And how the homomorphism, how is psi A defined? To map xi equal to A. This is obviously K algebra homomorphism. And kernel of psi A is precisely ideal generated by x1 minus a1, etc., xn minus a. These are very easy. These things are very easy to prove. Therefore, one can identify the points with this homomorphism, the K algebra homomorphism. So that means you can identify K power n with home K algebra homomorphism from the polynomial ring to K. And these are the ones, so the modulo that it will be K. So the residue fields are K. And that is precisely what I call it K spectrum. So K spectrum actually, if I write K spec A, this is a subset of SPM A, which is a subset of SPEC. This is by definition all those A in Kn such that all right, let me write it. These are precisely ideal generated by x1 minus a1, xn minus an, where a is a1 to a. Okay. And there are many of them. So they are like points. But you see, the maximal ideals may not be coming from points. We saw the example. And there are more prime ideals. So this is analog of the name comes spectrum because of this. And this and the spectrum one talks about in function analysis, they are similar. This is more general. Obviously, this came later than the spectrum in function analysis. I don't have much time to go over to make more remarks, but this is what it is. All right. So that is the spectrum. So I explained you what is the K spectrum. That is the number of points. So this was for the polynomial ring. Now, for the if you, A is not a polynomial ring and a finite dimensional vector space, then it is this. You can think of it is this sign. So those are the points. All right. So and let us come back to a theorem. So this connection is will give a way of counting the how many points in K spectrum has. I'm not talking about polynomial ring now. This was just a digression for the polynomial ring. Now, if you look at a finite K algebra, so that means A is our typical what we wanted to consider was this. Modulo ideal generated by F1 to F1. So in this case, R spectrum, R spec A, is precisely the zeros of this polynomial, common zeros of this polynomial. Given any point here, this belongs to this, if and only if. So this is if and only if Fj at A is 0 for all j from 1 to n. and this will give the maximal ideal in this, and it contains all these guys. Therefore, this this will this will be an element in R spectrum. And now, so even if you want to understand more precisely what you should do, let's take only one polynomial. And one polynomial in Rx, one polynomial, one variable. The algebra attached to that is this quotient algebra, Rx mod f. And what does it say if I relate that? So the B R of f, these are the zeros of f on one hand, number, and that is precisely the number of R spectrum, number of points in the R spectrum of Rx mod f. So that is R spectrum of A. And if I prove that this is equal to the signature of the trace form, then I will know how to count it. So therefore, our computation will reduce to computing the signature of the trace form. That is in progress. So it is a mixture of linear algebra with standard commutative. Standard means very basic commutative algebra, let's say, which you may need only a few earlier chapters of ATM. All right. All right. So our aim is to prove. I don't know how much I will be able to give the details, but my aim is to prove this thing. All right. So let's go on. Let me start proving the theorem, and we'll see. If I need some result, I'll go backward. The All right. So we know that symmetric bilinear form has decomposition. Decomposition means we saw that we can find a decomposition into if you take a orthogonal basis, then we get an orthogonal direct sum of those forms can be decomposed as orthogonal sums. All right, so similar thing I will do. All right, so we have this A. A is a finite algebra over a field. This algebra A I want to decompose into their local components. So this we want to decompose into local component means what? So you see this algebra A finite finite dimensional. So if I take the maximal ideals M1 to MR, then the Chinese remainder theorem will tell you A to A mod Mi is A mod M1 cross A mod MR is subjective map. And the kernel is precisely the intersection. This is Chinese remainder. So think of, so this was kx1 to xn, that our model example is this kx1 to xn. This is R modulo that f1 to fn. So this will decompose A. And so these are the field extensions. These are fields and they will all contain K, therefore these are the field extensions. And because we are in R, so the only field extension and they are algebraic extensions, so only R or C will appear. So few copies of R, few copies of C. And therefore the trace form, this will get decomposed into orthogonal sums. So trace of K, C, few times this, and these are the orthogonal sums. Few times C, and the remaining times R. This K is R. R over R. And therefore, when you want to compute the type of this form, just a type will be the sum of the other side. So type of ER, AR will be the sum. So this will be summation I equal to 1 to, I don't know how many number, R trace of R over, let me call it KI. So, where KI is either R or C. KI is C or R. And once you know the type, the type I forgot the type. Therefore, signature will be signature of the trace form will be sum of the signatures. Here is C or R. And I know what is the trace of R over R. So trace. So therefore, we have only to calculate. So only to compute two things. One, what is signature of trace of R over R, and second, signature of trace of C over R. If you know this, then we can compute the trace. That is easy. And what we can see easily, that this trace sign is 1 and this sign is 0. So this will correspond to the complex point and this will correspond to the real points. And that would prove our theorem. So that is the rough idea. But in this calculation, somewhere we will have to use. So that this you can easily do it. This I will leave it for you as an exercise. This C over R is an algebra, and we know the basis 1 and I, and here R over R, this is 1. Anyway, this is one-dimensional case, this is two-dimensional case, so you can easily do it. Okay, so what is more interesting, somewhere in this proof, you will have to use, there will be more trace forms, more general trace forms. So, for example, where, yes, the following theorem will be interesting. I don't want to go too much into generality, but so what this is what is called rigidity theorem. Rigidity theorem. This is a mixture of algebra and sort of analysis, topology, to be more precise. So let us take K equal to real numbers. So on finite dimensional vector spaces, etc., we will get a topology inherited from the usual top. And let us take the rational functions, Rij's. 1 less equal to I, j less equal to n. These are rational functions. One, a line connected open set. Open subset. U of R power n, capital N. Line connected is means that if you have 2 points, then the line connecting them is also completely continuous. That is what one means by the line connector. And assume that these Rij's are equal to Rji. Assume this. A rational function means one way to think is they are polynomial by polynomial. Where and therefore you are thinking them function so that their denominator should not vanish on the open set. That is what one means by rational function. All right. Then, and why do I assume this? Because look at the matrix. Matrix is what do I denote the matrix? Let's say MT. M at T. This is R I J T. Where T is an element in U. So for each element in T in U, we have a matrix. And this matrix has entries rational function. And assume again that determinant of MT is non-zero for all T in it. Then all these matrices, then the assertion is then type of this matrix MT then all ST values U have the same type. PQ. Same. In particular, or equivalently, same signature. I will prove this. Let us prove this because it's interesting shaping. All right. So proof. It is enough. This is not difficult. It is enough. Prove that the signature of these matrices MT is constant on the line segment L, which is completely contained. See, that is where assumption I needed U is line connected. See, U is here, and there is a line here. If I prove it is constant here, then it is constant everywhere. This is the standard argument one gives from topology. And because it's a line segment, we will assume it is this point to that point, so we will assume it is an interval. Our field is real number. Field is real number. And Rij's are rational functions. So Rij's are then Fij's, polynomial Fij by polynomial Gij. The Gij is non-zero. So 1 less equal to Ij less equal to n. And this is a non-zero point. And this denominator polynomial will never vanish on the interval. So Gij do not vanish on the interval AB. Actually, why call it AB? I could have called it 0 and 1. So even if one understands the particular case like this, you start with the rational function and take the interval, and suppose the down polynomials never vanish on that interval, then we want to say that these matrices which we have defined, they have the constant. The signature is constant on the line segment. All right. Now let us take G equal to the LCM of GH. These are the polynomials. And that's UFD. Therefore, LCM makes sense, and take that LCM. And because this Gij never vanish on this interval by intermediate value theorem, the G will have the same sign everywhere. G has the same sign on the interval 0, 1. The polynomial, and it can't have different signs on this interval, because otherwise it will cross and it will have a 0 on that. And that is not possible because we are assuming Gij are not vanishing on any point in the interval. And same sign, therefore, without loss, W without loss, we may assume that sign is positive. Positive sign. Positive sign. Sometimes it is confusing when we write this short form sign, that is sign of a real number or signature of the form. So that should be clear from the context. So because of this, if I take the new matrix, okay, so therefore, so this implies for every t in 0, 1, the original matrix, what did I call empty? Empty, empty, this matrix and Fij's, this matrix. Both are symmetric and they have the same signature. They have the same type. They have the same type. PQ. And therefore, if I evaluate this Fij at 0, their polynomial is 0, this matrix. Is congruent to the matrix, to the diagonal matrix. Few times P, A1 to AP, and then B1 to BQ. Where A's are positive and B's are negative. A's are bigger than 0, B's are less than 0. So this is for I is from 1 to P, and this I is from 1 to P. And P plus Q is N. It's non-degenerate. So what is Hurwitz criterion saying? If you look at the determinant, so let me put the principal manners DMT, which is, these are the principal manners, that is determinant of F I J T up to M. 1 less equal to I less equal to comma J less equal to M. These are the principal manners of this matrix. These are non-zero polynomials. These are non-zero polynomials. And the sequence, when you evaluate 0, D0, D1, 0, etc., DM0 has Q sign changes. This is what we proved in Hurwitz criteria by Hurwitz criteria. Now again, you can subdivide the interval and again do the similar thing again, use the Hurwitz criterion, and then you can conclude that. So conclude that these matrices Fi, J, T have for all T in 0, 1 have the same type. That is what we wanted to prove actually. So that proves the rigidity theorem, and this would have, if I would give more details about this trace form, etc., this will be used somewhere. But I don't want to drag in so much details. So this trace form is a tool to compute the type. And there are generalized forms of the trace form, and then you can use general compute. In this, I would stop my lecture because I don't want to get into more details of this. Anybody has questions, I would be happy to answer. Afternoon, we will do, therefore, the exercise 2 is there's so many problems about how does one compute the type and signature, etc. So, which will involve also intermediate value theorem and things like that. So that we will see in the afternoon tutorial session that there are more interesting exercises there also.
So, sir, lecture is complete?
Yes.
Okay, sir. So now we thank Professor Dilip Patil for the interesting and informative lectures on 23rd, 24 and today. He talked on trace forms and applications. We have learned a lot from his expository talks on this topic. We again thank him for spending his time and interacting with us. Thank you, sir.
Thank you. I also thank you for listening to me patiently.
Thank you.
And also I feel little sorry that I didn't give all the details, because then I will have had to do more commutative algebra, which is not appropriate in this advanced linear algebra school. Nobody has any question? And more details you can find in the you see, this was the joint work with Professor J.K. Verma, and that reprint also we have put in the Dropbox. No, Parnashi?
Sir, any references related to this?
Yeah, that is there.
Yes,
Parnashri,
Yes, sir.
Thank you.
that paper you have put in the Dropbox, no?
Yeah, I have put it. Yes.
So there